Earlier, we used a chi-square goodness of fit test to test the distribution of one categorical variable. This is a different chi-squared test called a chi-squared test of independence, and this is used to test the relationship between two categorical variables. Okay, so the null hypothesis for chi-squared test of independence is that there is no relationship between the two variables. So if we put it in context here, we could say, and this is going back to that jam choices context, that the size of the choice set is not related to customers stopping. So whether they stop or not has nothing to do with whether they saw 6 choices of jams or 24. So obviously we don't need a test to tell us what happens in the sample, right? We already know that there's an association in the sample. So this is about what is going on in the population, right? Is there a long run relationship between these two variables? Okay, and then the alternative is that the size of the choice set is related to customer stopping, and again in the population. And this is generally always done as a two-sided test. Chi-squared tests are two-sided. So we're not saying right now whether it's making it better or worse, whether it's making more customers stop or fewer. We're just saying, is there a relationship between the two? Okay. So chi-squared tests work by comparing observed counts to expected counts, and those were pretty easy to calculate in a goodness of fit context. It's a little bit trickier here. So when we say expected counts, we mean what would you expect if there were really no relationship between these two, right? So basically you're saying that choice set doesn't matter, it makes no difference in the proportion who stop. So you can sort of think about, okay, well, if it really made no difference, then you could take the overall proportion who stop, overall proportion who stop. So that is, if we look at the totals down here, that would be 161 out of 320. So about 50%, just a coincidence that it came out so close to 50-50. And you would expect that that would apply to both of your groups, right? So let's say that we wanted to look at the proportion who stopped in the small choice set group. Okay, so we would expect that out of those 157, about half of them would stop, right? So 50.31% of 157 would be 78.99, and this would be the number we'd expect to stop in the small choice set group. So again, whenever we say expected, we mean what we would expect if the null were true. Here, what we would expect if there were really no relationship. So you can sort of reason it out that way, but there's also a formula for the expected counts. So to get the expected count, we can take the row total and multiply it by the column total and divide that by the overall total. So let's find those numbers here. So again, if we're talking about the number who stopped in the small group, we would be taking the row total times the column total divided by the overall total. So 157 times 161 divided by 320. And if you look at it, that's actually the same as the numbers that we used up here, right? So this is just a way of getting there without having to like reason it out each time. Also, you can have JMP do this for you. So one of the options that you can choose from the contingency table when you click the little down arrow is expected, and that's going to give you the expected counts for each category. So the formula for the expected counts was different, but the chi-squared statistic formula is actually the same. So it's still a way to compare the observed counts, so that's your sample data, your actual sample, with what you would expect. And you're talking about what you would expect if the null hypothesis were true, which in this case, the null being true means if there were really no association between the variables. Okay? So let's just write out a couple of these. So I'm going to start with this first cell here. So it would be observed is 63, that's the actual count, minus the expected is 78.9906 squared all over 78.9906. And I'm going to be lazy and skip ahead to the last cell down here. So the observed count was 65. The expected was 80.9906. So you would be adding this up for all 4 cells. I'm just going to be a little bit lazy about writing it all out. Right? And so then we end up with a chi-squared statistic 12.790. So we know that the larger the chi-squared statistic is, the stronger the evidence, right? The stronger the evidence that there really is an association between the variables. But before we can decide if this is large enough to be convincing, we have to compare it to something, right? We have to compare it to a chi-square distribution. And remember, there's different versions of the chi-square distribution depending on the degrees of freedom. So a chi-square test of independence has a new formula for the degrees of freedom. It's going to be the number of rows minus 1 times the number of columns minus 1. And by the way, this formula is given on your reference sheet, so you don't have to worry about memorizing it. So when we say the number of rows, we're not including totals. So here it would be 2 minus 1 times 2 minus 1. So this is actually just 1 degree of freedom. So when we talk about number of rows, maybe I'll put a note here, don't count the totals. Okay, so that's the logic behind a chi-squared test of independence. In the next video, I'll show you how to calculate the p-values using JUMP, and just like before, there's 2 different ways to do that.